Okay, so this is lesson 8 of Unit 2. So we started today with a warm-up. So there's the warm-up. Take a moment, pause the video, try the warm-up problems, and then play to check your answers. Okay. So let's see here. I can go over the answers for the warm-up. So the first problem, we have a 2x2 and a 2x1, which means we get a 2x1 when we multiply. And I'm doing row 1 by column 1, 1 times 1, 2 times 2, adding to get 5. Then this is the 2 1 spot, so second row, first column, 3 times 1, 4 times 2, add gives us 11 for the second spot. The second problem, find AB. AB is a 2, or A is a 2x2, B is a 3x2. The inner dimensions do not match up, so AB is not possible or undefined. Okay, but on the other hand, BA, 3x2 first, 2x2 second, that is possible. AB is undefined. So BA, writing down the 3x2 first and the 2x2 second gives us a 3x2. So the 1, 1 comes from 1 times 1 and 2 times 5 added together is 11. The 1, 2 comes from 1 times 3 and 2 times 8 added together. The 2, 1 comes from 4 times 1 and 1 times 5 added together. The 2, 2 comes from 4 times 3 and 1 times 8 added together. The 3, 1 comes from 0 times 1 and 5 times 5 added together. And the 3, 2 comes from 0 times 3 and 5 times 8, which is 40. So that is our product. Okay, so that takes care of the warm-up. So then today we discussed how to find what's called the determinant and also what's called the inverse of matrices. Now today was really just the basics. How do we find the determinant? How do we find the inverse? I did not really get into what is a determinant other than just how to find it. And I didn't really get into what is an inverse that much other than how to find it. We'll get into that in the next several lessons. But for now, we really just care about how do we find the determinant, the basics here. How do we find the determinant? How do we find the inverse? And then we'll talk about the whys in the next couple of lessons. So the determinant, when we see that we're supposed to find the determinant, there's a couple of ways that you can tell that we're looking for the determinant. Sometimes the notation used will be DET. Let's say I called this matrix D. If I called it matrix D, then I'd write the DET of D, determinant of D, and that would indicate that I was looking for the determinant. Another way of notating that I want the determinant is by taking the brackets away from the matrix and instead putting bars, almost like absolute value bars, and then putting the matrix inside of those bars. When you see that notation, we have a bracket and the matrix inside of it, not bracket, we have those bars and the matrix inside. That means find the determinant of this matrix. Okay, so either DET of the matrix or just in the bars. Either way, we know to find the determinant. So here's how we find the determinant. The determinant is found for a 2x2 matrix like this one is by multiplying the numbers in that diagonal. So when I do that, I'm getting 3. And then subtracting the numbers that we get from the other diagonal multiplied. So 0 times -4 gives us 0. When I subtract 3 minus 0, I get 3. So the determinant of that matrix is 3. Next, we're going to find the determinant of this matrix. So once again, we could say DET, or I'll just put 2, 1, negative 1, 3 inside of those bars. And I know that I'm going to do 2 times 3 is 6, and I'm going to subtract negative 1 times 1, which is negative 1. So that gives me 6 plus 1, which is 7. Next, we found the determinant of 3 by 3 matrices. So we talked about in class the fact that determinants can only be found if the matrices are square. Square meaning that they have the same number of rows as they do columns. So if the matrix is square, then a determinant can be found. So we just looked at the 2 by 2 matrix, which was square. Now we're going to look at the 3 by 3 matrix and find the determinant of that. So when we want to find the determinant, it's a 3 by 3, it's a little bit more complicated because I can't just go down the diagonal and up the diagonal like I did in the other matrix. If I were to do that, there'd be numbers that would be left out and not included in those diagonals. So to avoid that problem and to use all of the numbers in the matrix, what we'll do is we'll copy the first 2 columns right beside the matrix. So copy just the first 2 columns. Now I have enough rows and columns that I should be able to look at the diagonals going down and also going up. And then I'll multiply, just like we did on the 2 by 2. So I have 1 times negative 4 times negative 1, which is 4. I have 2 times 1 times 0, which is 0. I have 3 times 0 times 3, which is 0. I'm going to add those numbers, and when I do that, I'm getting 4. Now I'm going to go up the diagonals. 0 times negative 4 is times 3 is 0. 3 times 1 times 1 is 3, and negative 1 times 0 times 2 is 0. I'm adding those, and again, I get 3. Now, just like what we did in the 2 by 2, after we got the diagonal, we subtracted them. I'm going to do that here with these sums of the diagonals. So I'm going to subtract 4 minus 3, and the determinant is 4 minus 3, which is 1. So you try this one. Find the determinant of this matrix. Again, pause the video here, try it, and then check your work. Okay, so I'm going to give it a shot. So 5, 0, 2, negative 2, 3, 0. That gets copied. And then I'm going down the column, or down the diagonals, and up the diagonals. So I have 5 times 3 times 7, which is 105. I have negative 2 times negative 1 times 2, which is positive 4. I have 1 times 0, which is 0. When I add, I'm getting 109. Going up the diagonals, 2 times 3 times 1 is 6. 0 times negative 1 times 5 is 0. And 7 times 0 times negative 2 is 0. When I add, I'm getting 6. So the determinant is 109 minus 6, which is 103. Okay, so that takes care of determinant. Now we're going to take a look at the next concept for today, which is called the inverse. So I have this matrix here and I'm going to find the inverse of it. Now, let's just say I'm naming this matrix A. So if I have matrix A and I want to find the inverse of it, we'll talk about the notation that we would use. The notation we would use is an A raised to the negative 1 power. Now, when we read that, we don't say A to the negative 1 power, we say A inverse, okay? So you see that notation, it is indicating the inverse. So A inverse. So A inverse we get by, first of all, figuring out the determinant, and then when we have that determinant of A, we're going to put it as a fraction, and we're going to put that determinant in the denominator of the fraction. And the numerator of the fraction should be a 1. So then I'm going to take that number, whatever 1 divided by the determinant of A is, and I'm going to multiply it by a matrix. And it's just going to be like a scalar, multiplying by everything in that matrix. The matrix we multiply by is an alteration of the original. A and D switch spots. And B and C, they stay where they are, but they change signs. So if they were positive, they become negative. If they were negative, they become positive. So once we have switched the spots and changed the signs on A, B, C, and D, we are going to multiply each one of those numbers by 1 divided by the determinant of A. So I can simplify that a little bit. We know from the previous problems that the determinant of A would be A times D minus B times C. So I can rewrite that as AD minus BC. And then that's going to be multiplied by D, negative B, negative C, and A. Okay. So I'm just going to leave it that way, but I could multiply it out. I'd have D over AD minus BC. I'd have negative B over AD minus BC. I'd have negative C over AD minus BC. And I'd have A over AD minus BC. And that's all in a 2 by 2 matrix. Okay, so that's my result there. So we're going to find the inverse of A, which is called A inverse. So we're first going to figure out the determinant. And we're going to put that under 1. So 1 over 4 minus 6. And we're going to multiply that by the 4 and the 1 swap, the 2 and the 3 stay, but change signs. So that's negative 1/2 times 4, negative 2, negative 3, and 1, which gives me 4 times negative 1/2 we know is negative 2. Negative 2 times negative 1/2 is positive 1. Negative 3 times negative 1/2 is positive 3/2. And 1 times negative 1/2 is negative 1/2. So that is A inverse. Okay. So that takes care of inverse. Next, does an inverse exist? So I want to point out that sometimes matrices do not have an inverse. Okay, and so we're going to figure out when that is. So I'm going to go back a moment just to the previous slide, and we'll look at the process for finding the inverse. So remember, I said a moment ago that you take the determinant of A and you put that in the denominator. And then that fraction gets multiplied by all the other numbers in the matrix. Well, if you think about that, if the denominator here is equal to 0, then I'll be trying to divide 1 by 0. And we know that that's undefined. So the denominator cannot equal 0. Otherwise, we would not have an inverse. So when I'm trying to determine whether the matrix has an inverse or not, all I have to do is to find the determinant. And if the determinant is 0, then the matrix does not have an inverse. And if the determinant is any number besides 0, then the matrix does have an inverse. So we'll go back to our problem now. And you should probably jot that in your notes, that if determinant is equal to 0, then no inverse exists. If determinant is not equal to 0, then an inverse exists. So we're going to try it on this one. I'm going to get the determinant. 2 times 4 is 8, minus 1 times 8, so 8 minus 8 does equal 0, which means does an inverse exist for this particular matrix? No, it does not. Okay. Next, another matrix here. We're going to figure out if an inverse exists, and if it does, we're going to find it. So first, we're going to figure out if it exists. So 2 times 4 is 8. And negative 2 times 6 is negative 12. And we're subtracting negative 12. So that gives me 20. 8 plus 12 is 20. Whoops, I don't know why I wrote 80. 20. So that is the determinant. So because 20 is not 0, then that means yes, B inverse does exist. So now we'll find it. So B inverse, I'm going to first put 1 over the determinant, which we just got as 20, times the matrix where I flip the 4 and the 2, and I change the signs on the 6 and the negative 2. So the 6 becomes negative and the negative 2 becomes positive 2. Now I'm ready to multiply. So 1/20th times 4 is 4/20ths or 1/5. Negative 6 times 1/20th is negative 6/20ths or negative 3/10ths. 2 times 1/20th, 2/20ths or 1/10th. And again, 2 times 1/20th is 1/10. So we have 1/5, negative 3/10ths, 1/10, and 1/10 for B inverse. Okay. And the last thing we need to look at today. So proving that these two matrices are inverses. All right, so one way that I could prove that they're inverses is simply just to find the inverse of the one on the left and show that it's the one on the right. And then vice versa, find the inverse of the one on the right and show that it's the one on the left. So that's one way. And we certainly could do it that way, and that would be correct. Another way, though, is thinking about what an inverse is. Okay, so I have to kind of explain that a little bit. And to explain that, I'm going to just talk about numbers for a moment. So if I have a number, 5, and I look at its multiplicative inverse. Okay, well, multiplicative inverse is a fancy way of saying reciprocal. So its reciprocal or multiplicative inverse is 1/5. Well, if I multiply that number times its multiplicative inverse, I will get 1, always, regardless of the order. If I multiply 1/5 times 5 in that order, I still get 1. Well, 1, you learned early on in math, has a special name. It is called the identity. Specifically, identity. Specifically, it's called the multiplicative identity, because when I multiply a number by 1, I get the number back. So identity means self. So if we take a number times the identity, which is 1, we get the same number back. So back to the math here, when we have a number and we multiply it by its multiplicative inverse, we get 1, which is the multiplicative identity. Similarly, with matrices, when I have a matrix, let's just call this, I don't know, F. And if this here is its inverse, F inverse, when I multiply the two, F times F inverse, I will get, it's not going to be a 1, but it's going to be the multiplicative identity for matrices, which we call I. So the multiplicative identity in numbers is the number 1. Well, the multiplicative identity in matrices is the matrix that looks like that. Okay, that is the identity matrix for 2 by 2 matrices. 3 by 3, we'll talk about that later, but the 3 by 3 looks a little bit different. But for 2 by 2, we have 1s in this diagonal and we have 0s everywhere else. So that is the identity matrix. So if these are inverses, when I multiply them, I should get the identity matrix. And when I reverse the order, I still should get the identity matrix. Okay, if they're inverses. Now, we talked earlier about the fact that with multiplication of matrices, normally the order matters. A matrix A times a matrix B is not the same thing as matrix B times A, normally. But if the two matrices are inverses, then the order doesn't matter because you'll still end up with the identity matrix. So what we're going to do, we're going to practice our multiplying here since we just learned that yesterday. We're going to get a little practice multiplying matrices. So I'm going to do them in the order they're written first, multiplying. And then I'll flip around the order and I'll multiply. and we'll see what we get as a product. So a 2 by 2 times a 2 by 2 is a 2 by 2. So we're going to go here one at a time, row by column. 5 times 2 is 10, minus 1 times 9 is 10 minus 9, which is 1. 5 times 1, minus 1 times 5, 5 minus 5 is 0. Negative 9 times 2 plus 2 times 9, so negative 18 plus 18 is 0. And negative 9 times 1, negative 9, plus 2 times 5 is 10. 10 minus 9 is 1. So we did get the identity matrix there. Here, row by column, 2 times 5, 10 minus 1 times 9, 10 minus 9 is 1. Next, 1, 2, 2 times negative 1, 2 plus 2 times 1 is 2. Negative 2 plus 2 gives me 0. Next, 9 times 5, 45, plus 5 times negative 9. So 45 minus 45 gives me 0. And lastly, 9 times negative 1, negative 9, plus 5 times 2 is 10. 10 plus negative 9 is 1. So both directions, multiplying either way, we are getting the identity matrix, which means that we just proved that these two matrices are inverses. Yes, they are inverses. And again, our proof is right here. Okay, when we multiplied the matrices together in either order, we did end up with the identity matrix, which means they are inverses. So, homework for tonight, pages 22, 23, and 25, all that are on those pages, they're short problems. They should not take long. And page 24, you'll see two columns, a column of problems on the left and a column of problems on the right. I'd like you to do the column of problems that are on the left-hand side only of page 24.